So I have the honor of kicking off our Talking Tall lecture series tonight, created in partnership with the Council on Tall Buildings, Urban Habitat, and sponsored by the Softwood Lumber Board. We are grateful for your partnership and months of collaboration. And we've been partners the whole way in constructing an exhibit as well as crafting this lecture series that we hope you'll be attending for the future months to come. I also want to thank our panelists for their role in guiding the conversation. And I want to welcome our Zoom audience. I believe we have close to 200 people on Zoom who are joining us tonight. I'm sure I don't have to tell you just how revolutionary mass timber is as a building material. It offers so much potential for decarbonization, sustainable development, and healthier cities. And the CAC is honored to play a role in presenting these benefits of mass timber to a broader public. So let's get started with presentations and a panel discussion on the mass timber sector and its momentum in North America. I'm pleased to introduce Paul Alessandro as our moderator tonight. Paul and I have worked together for many years, and he is a partner at Hartshire & Plunkett Architecture with more than 25 years of experience designing complex projects. He has led the firm's preservation group, and his award-winning historic projects include the Chicago Athletic Association Hotel and Randolph Tower City Apartments, Chicago's tallest terracotta-clad tower. He most recently oversaw the renovation and landmarking of the Essex Inn Hotel and 56-story residential tower addition, Essex on the Park. Paul also helps lead HPA's growing body of research and built work in mass timber. So please help me welcome Paul to the stage.
Thank you, Eleanor. As she said, it's been a lot of years. Good evening, everyone, and welcome to the REFRAMED, the lecture, The Future in the Cities of Wood, the introductory companion discussion to the Chicago Architecture Center's newest exhibit, Talking Timber, Can Wood Save Us? The exhibit explores the positive aspects of building with mass timber, its sustainability and safety, which is a doubly resonant topic for those of us who live in Chicago. I'd also like to welcome our online participants this evening again. At the conclusion of our panel's discussion and presentations, we'll be taking questions from our in-person audience as well as those online. Since we want to leave as much time as we can, let me introduce tonight's presenters in the order they'll be speaking. Starting on my right is Ricky McLean. With his extensive experience as a lead engineer in roles related to structural design, project management, and construction administration, he is the in-house expert on tall buildings, tall wood buildings and woodworks. He provides analysis, guidance, and educational resources on architectural, fire, life safety, and structural design topics related to tall mass timber projects. Next is William Broderick, serving as area sales manager to the Great Lakes region. William carries Rotho Blase's expertise in the wood carpentry industry from the heart of the Italian Alps to the US. He regularly networks with architects, engineers, and professional builders interested in using innovative European technical solutions for mass timber construction, timber frame, and wood frame buildings. Kevin Hyland is the UL Solutions Principal Engineer for Fire Resistance and Containment within the built environment. He represents UL Solutions Standards Committee across the region and in key industry association memberships. In his 25 years with UL Solutions, he's managed many of the most complex, large-scale fire certification projects around. Catherine Joseph is an architect with 3XN and leads the firm's North American project teams, as well as helping lead their New York studio. Much of her work focuses on large, complex urban projects, including the mass timber T3 Bayside office building in Toronto that we will explore tonight, among others, including a confidential high-rise currently in development. Finally, we have Leif Johnson, who is the structural engineering director at StructureCraft. Leif is a licensed structural engineer with over 16 years of experience designing high-profile museums, civic structures, and performing arts centers throughout the United States. Prior to his current position, he was a principal of Magnus and Klemensic Associates Cultural Group and led the timber technical safety team at MKA's Seattle office. And with that, I will turn it over to Ricky to start our conversation.
All right, thank you, Paul. All right, welcome everybody. As Paul mentioned, my name is Ricky McLean. I'm with Woodworks. And for those who aren't familiar, Woodworks is a nonprofit organization. We're based here in the US and cover the entire US. We provide free project assistance on light wood frame projects, as well as mass timber projects. And we do that through one-on-one technical assistance, as well as education. Essentially, we are a free resource to any of you architects, structural engineers, developers, and contractors. And we are able to do this for free because of the funding of our funding partners, the support of our funding partners, the Softwood Lumber Board, USDA Forest Service, and Forestry Innovation Investment. Over the next 5 minutes or so, I'm going to take us on a very brief timeline to essentially help us understand how did we get to where we are today with mass timber. So if we look back just 12 years ago, this small 2-story, 10,000 square foot project in Montana was the first commercial, the first use of CLT in a commercial application. So that was just 12 years ago. Fast forward 11 years from that, or last year, what was completed was the tallest mass timber building in the world, located just a couple of hours from us in Milwaukee, the Ascent Tower. So a very rapid progression, 11 years going from the first application in a commercial building to the tallest mass timber building in the world. So what was that journey like? How did we essentially arrive where we are today with mass timber? I think anytime that we look at domestic use and innovation associated with mass timber, we have to first acknowledge the innovation and inspiration that we do draw from those internationally. Mass timber has been used longer internationally than it has been here in the US. And looking at some of these projects that you see here in Europe, in the UK, in Australia, and then in Canada, there was a lot of innovation going on that really inspired a lot of the domestic designers, architects, and developers to use mass timber at scale, at large, tall projects. So you can see some of those projects here starting in 2014 and 2015, and then accelerating to 2017 with the 8-story Carbon 12 project, which was the first completed tall mass timber building in the US. Really going hand in hand with those advancements with the projects themselves that were happening was advancements on the code front. The International Code Council, ICC, developed a committee to essentially assess the feasibility of should they allow, prescriptively recognize and allow the use of mass timber on projects in excess of 6 stories. Now, that is based on this 3-year code adoption cycle. So the 2015 version of the IBC was the first version of IBC that really recognized at all the use of CLT as a allowable building material, CLT cross-laminated timber. But it only allowed it at heights of 5 or 6 stories, depending on the occupancy. That was also the case with the 2018 IBC. The 2021 IBC was the first version that prescriptively allowed much taller mass timber buildings. And that recognition, the change in the building code, was very closely tied to the work that the ICC committee was doing, notably full-scale compartment fire testing. So what you're seeing on the screen here is a 2-story compartment fire test that was done to simulate an apartment building loaded up with combustible contents. Those contents were, as you can see here, started on fire. No sprinkler activation was done. No fire service personnel intervened. And this was the result. They basically allowed the contents to completely burn out, with the goal of seeing, is the mass timber structure that surrounds this and in certain test scenarios exposed to some level, is that safe, structurally sound, and able to withstand full compartment fire burnout? So those tests were very successful and led to a series of code changes in the 2021 IBC that again allowed much taller mass timber buildings up to 18 stories. What followed that was a second round of full-scale fire testing, this time with a newer generation of adhesives used in the mass timber products, to again evaluate the amounts of timber that could be exposed in these high-rise mass timber buildings. Another round of successful fire tests led to another round of code changes. So what's now going to be allowed in the 2024 version of IBC, which is set to be published at the end of this year, is 100% timber ceiling exposure on projects up to 12 stories in height. You can still do mass timber up to 18 stories, but if you go above 12 stories, there are some prescriptive limitations in terms of the amount of timber that can be exposed. And of course, those codes are great, but if they're not implemented and adopted, it's going to slow down some of the timber and project use. So we are seeing a rapid acceleration as well as with the adoption of those codes. As you can see on this map here, basically any state that's not dark gray has some level of prescriptive tall mass timber code recognition or adoption to allow those projects to take place prescriptively. It's not to say that projects are only limited to those locations, but this is where the prescriptive recognition exists. And then, of course, we saw kind of the testing that led to code changes, which lead to projects. And so just to highlight some of the innovative projects that are happening across the US right now, the 9-story one of Paul's firm's projects in Cleveland called Intro, about 500,000 square feet, 300 apartment units. Project that just broke ground in Madison, 15 stories called Baker's Place. This is set to be mass timber multifamily. A really exciting project and trend that we're seeing is more use of mass timber in affordable housing projects. So this is an 8-story from grade mass timber project in Portland, Oregon. And then this really is just kind of summing up all of what I said, showing that rapid acceleration and growth, where you can see the chart on that lower left is showing the number of projects by year. And then you can see starting in about 2015, 2016, that rapid acceleration to the point where now we're looking at about 1,750 mass timber projects all throughout the US. You can see they are spread quite geographically spread throughout the country. So that's essentially where we are today. We do have a lot of resources on the Woodworks website, as well as a really innovative tool that allows you to search project locations, interactive map, where you can learn a lot more about these projects that we've talked about on the Woodworks Innovation Network. So with that, I will turn it over to Bill. Thank you.
Thank you, Ricky. We only get 5 minutes, so there's no time for lollygagging here. I'm just going to jump right in, and I'm going to very quickly kind of highlight some of the other materials besides wood that are utilized in tall modern timber buildings. Our quick backstory at Rotoblas is our founder started out distributing high-end wood cutting tools, and he was going to his customers. They didn't like the screws that are available in the marketplace at the time. So like a good entrepreneur, he went out, hired some engineers, and started building better screws. Over the years, the cross-laminated timber industry has developed in and around the Alps, where we're headquartered. And there's now a bit of a mass timber technology cluster in the Northern Italy, Austria, Switzerland area. Today, we have nearly 600 employees at Rotoblas in 90 countries. We help architects, engineers, developers, and contractors. We've probably been involved in one way or another with over 85% of all the mass timber projects around the world. At Rotoblas, our materials focus on the connections, air tightness and waterproofing, sound attenuation, fall protection, and we also provide tools for the contractors to address some on-site issues such as wood cutting, lifting, and water management. All right, so let's take a look at some of those other non-wood materials. Let's see. Steel might not be very exciting, but there can literally be hundreds of thousands or maybe even 1 million or more carbon steel screws hidden inside of a tall timber project. These screws are optimized for a quick grip, ease of progress, and fast insertion into the wood, excuse me, and depend on the type of the wood species that are being utilized on the particular project. With steel annealing and tempering processes these days, modern timber screws strike that balance between resistance and ductility. The Spider is on display in the other room here, is a innovative steel column-to-column connector that allows designers to decrease the size of structural columns, yet increase the spacing between the columns to create some fairly dramatic open space using timber. It allows the construction of multi-story buildings with column-to-floor structure. Like most of our products at Rotoblas, it's going to be fully concealed underneath the floor assembly. It's certified, calculated, and optimized for use with a glulam, LVL, steel, or a reinforced concrete column. The steel core of the Spider system prevents the CLT floor panels from being crushed and allows the weight of the vertical load to be transferred efficiently between the columns. The arms of the Spider system ensure the punching shear reinforcement of the panels, resulting in exceptional shear strength. But again, the key architectural key of the Spider is it increases the column spaces and allows spans greater than 22 feet between columns. Concrete is often utilized in timber buildings. In there, we're developing a system with the University of Innsbruck to fuse CLT panels with reinforced concrete. This joint will be certified later this year to transfer high stresses from timber elements to concrete elements, such as maybe a core, a foundation, or as pictured here, a connection joint between panels. With the right design, both a moment resisting connection and a hinge connection can be achieved with this. For timber to timber, timber to steel, and timber to concrete connections, extruded aluminum is often utilized for a weld-free, lightweight, yet high-strength, cost-effective connection. It's being utilized in our new Alomega connection, which is aluminum connection that has a high capacity beam load up to 90 kips. Taking a look at some of the softer materials that are utilized in timber buildings, we get a shout out to all the polys in the house. There's polyurethanes, polyamides, polyester, polyethylenes, polypropylenes, butyls, bitumens, and acrylics. All these materials are still necessary in the envelope of a timber building to handle the various stresses that the building might encounter, such as various chemicals, mechanical stress, ultraviolet stress, water, and of course, fire. Let's see, orchestras are made of wood because wood is an excellent transmitter of sound. So timber buildings need to be designed to address acoustics. Various materials such as recycled pre and post consumer wastes, fibers and textiles can be woven to create sound mats to address impact and airborne noises in a timber structure. But the structural elements themselves need to be disconnected from each other to prevent vibrations passing throughout the structure itself. So called flanking transmission. We're a leader in developing solution for these flanking sounds using materials such as monolithic polyurethane, EPDMs, and even cork can be utilized to address some flanking sounds. When it comes to sustainability, our facilities, we use renewable energy, electric vehicles, and reducing volumes of materials used in our packaging, developing new life cycle assessments for all our products, adding those nearly monthly to our product offering there. But our showpiece example of our commitment to the mass timber industry is what we think is the largest fully automated mass timber warehouse in the world, utilizing locally sourced CLT in the walls and a glue lime racking system, which supports the structure itself. It's a robotic stock picking system that more than doubled the capacity of our main warehouse and headquarters in Italy there. So that was your short attention span rundown of where steel, aluminum, concrete, plastics, and textiles can be used in a modern wood building. So thanks for the time.
All right. Hello, everybody. Can you hear me okay? All right. My name is Kevin Highland. I'll be talking about fire safety and fire safety of mass timber. But before we get to that, I'd like to share some recent news about UL. Last year, the UL Enterprise announced new brands for our three organizations: UL Research Institute, UL Standards and Engagement, and UL Solutions. Each contribute to our common mission, working for a safer world. So the UL that you know for testing and certifying products, we are now known as UL Solutions, a new brand with the same mission, bringing safety science to life. Okay, so back to fire safety. There should be a comprehensive or balanced approach to fire protection, not just active measures of fire protection like sprinklers and smoke alarms, but also what's called passive fire protection. What passive fire protection is build or systems and products that work to contain a fire to the room of origin. So when we contain a fire or compartmentalize a fire, we use fire resistance rated walls and floors to contain the fire to the room of origin for a certain amount of time. So in this picture here, we see that there's a fire on the lower floor. So if the wall and the ceiling and the floor are built a certain way, they can contain the fire to that room of origin for a certain amount of time. So how do we know if that wall or ceiling will effectively contain that floor? Well, there's the test standard, UL 263, ASTM E119, fire test of building construction and materials. In that test standard, it provides a means of evaluating the fire resistance of all building components: beams, joists, columns, floors, roofs, and walls. So let's look at that test standard. Let's look at how you conduct a fire test on a floor. So let's do that. We're talking about mass timber today, so let's do that with CLT, cross-laminated timber. CLT is typically consists of nominal 2x4 lumber laid down in multiple layers in a crisscross pattern and glued together or laminated together. That's CLT, cross-laminated timber. All right, so now that we've built our CLT slab, let's test it per this standard. Let's, on the left side here is our test furnace, and on the right side is our frame. So let's put in 4 CLT slabs there, side by side. Now this is a full-scale test. This floor is 14 feet wide by about 17 feet long. So it's big enough for someone to stand on and walk on. So now that we've built our floor, let's put that on top of the furnace. And then let's prepare the top side for the test. So on the top side during the test, we're going to measure temperature. That's done with 9 thermocouples, each covered by a ceramic pad. And then we're going to load the floor with 16 steel tanks filled with water. The level of water in each tank dictates how heavy it is, and the standard tells us that we need to load the floor to its maximum capacity. Okay, so that's the top side. We're done with that. Now let's look underneath the floor. That's where the fire will be inside the furnace. Let's take a closer look there. So how hot will it get inside this furnace during the test? The temperatures inside the furnace follow what's called the time temperature curve shown here on the right. At 5 minutes into the test, the furnace will be 1,000 degrees Fahrenheit. And at 1 hour, the temperatures inside the furnace will be 1,700 degrees Fahrenheit. Okay, so that's the test setup. How do we know if our floor will pass the test or not? What's the acceptance criteria? There's 3 of them. The first is that the CLT floor has to prevent openings and passage of flame. The second is a temperature rise limit on the top surface. And then the third and final one is that the floor has to maintain the applied load during the test. Whichever of these 3 criteria is reached first, the test is considered over, and the floor is assigned an hourly rating based on the time that that criteria was reached. Okay, so that's the fire test method. Let's take out our CLT slab and look at another way to determine the fire resistance of CLT. That is a calculation method. This follows the test that Ricky described earlier, the compartment test that got into the building code. So you don't have to do that fire test anymore now that I just described, but this calculation method has its foundations in that fire test. So it's in the building code in section 722 of the IBC International Building Code, and that allows fire resistance of exposed wood in accordance with the NDS Chapter 16. In NDS Chapter 16, it assumes a nominal char rate of 1.5 inches per hour for all CLT, and it assigns what's called effective char depths. There's also an industry document called APA PRG 320 that looks at the elevated temperature performance of the adhesive, the glue that's used in CLT. If you want to read more about this, an excellent resource from the AWC, American Wood Council, is NDS Technical Report number 10. Okay, so let's actually do a calculation example. Let's see how this works. So let's say you have a CLT floor of a ply, as shown here, 5 plies, 5 layers, made of nominal 2x4 lumber, a total thickness of 6 7/8 inch. It's grade V2. Our design load is known, and we need a 60-minute fire rating. So if we go through the building code and that NDS Chapter 16, it tells us that the effective char depth for this particular layup is 1.9 inches. So let's burn away, in theory, in our calculation, let's burn away 1.9 inches of this CLT starting from the bottom. So now the key here is that when wood burns, it forms a protective char layer that slows down the progression of fire through the wood. So as we burn away 1.9 inches, that takes away the bottom layer completely. And if we keep going, that takes away partially the second layer. Well, the calculation says you can omit that partially burned second layer to make this calculation simpler. So now you're left with these 3 layers that in theory are untouched by the fire. So all you have to do now is a load calculation to see if these 3 remaining layers can support the needed load. Another way to look at this, to describe this, is that those bottom 2 layers that we just burned away, Those are the sacrificial layers, and these top 3 layers are the ones that are actually providing the required load. So lastly, one other area for fire safety for CLT is fire stop systems. So let's say we have our same CLT floor slab here, and we need to put a hole in it to put a pipe through it for plumbing, as shown here. That space, the gap there, that annular space between the pipe and the CLT floor, that needs to be filled with the fire stopping material to prevent fire and heat from coming in through that space. There is a test standard for that. It's not a calculation method at the moment, but the fire test for that is UL 1479. It's similar to that test we looked at a bit ago, but it's done on a much smaller scale. UL Solutions has made it easier for architects to find these fire stop solutions. On our online certification directory, Product IQ, in the fire stop systems search, we have recently added a drop down for CLT floor assemblies to make it easier to jump to those and find those. So thank you. Thank you.
Thank you. Is this working? Cool. Thank you to the Chicago Architecture Center for inviting 3XN to be here. And I also want to give a shout out to Heinz, who is our partner in developing T3 Bayside. They're really the reason we're here. So for those who don't know 3XN, we're a Copenhagen-based architecture firm. We have 5 studios globally. We work across typologies and across geographies. And our approach to design really supports and necessitates a close collaboration with GXN, which is our research and innovation consultancy. Today, I'm going to take you pretty quickly through 4 of our transformational projects, focusing on mass timber, of course, but also on projects that focus on activating public space, that treat the workplace as a community, that sort of rethink public amenity on the waterfront, and also that rethink how we can design for carbon in other ways. So T3 Bayside, of course, this is the project that's in the exhibition behind us. This is a pair of buildings, actually, in Queens Quay neighborhood on the shore of Lake Ontario in Toronto. The first of the buildings is under construction now, with the first tenants moving in later this year. The focus of these projects was on the public space between them. The design of the buildings as a pair really is intended to activate the public space and really draw that public activity up into the buildings. This is achieved through a series of steps. First, the steps that are located on the public space, but then a series of double height spaces that take you up through the building, both public and sort of commercial space, creating a necklace of activity around the project. Here, we're looking from one building across the public plaza into the public space in the other building. And so these double height spaces are really intended to be places of collaboration, of sort of social interaction. They've also been designed flexibly so that throughout the life of the building, sort of knockout slabs or deconstructible slabs can be added in and taken out to provide optionality to tenants over the course of the building's lifetime. The project is constructed of sort of a standard gravity system, beams and columns and slabs. It is a 2-hour rated CLT system. We have been able to expose the entire structure, so all of the timber is exposed in the building. And the use of mass timber in this project resulted in a 40 to 50% reduction in embodied carbon. And so here you can see one of the tenant spaces that is ready for occupancy in a few months, which is very exciting. The next project is located in Denmark. The Cobot Hub is a new headquarters for 2 independent robotics companies. These companies really have focused a lot on how they collaborate within their departments, but also with each other across the 2 different entities. And so the design has created a series of neighborhoods throughout the building that allow for this cross collaboration and sort of observation of interdisciplinary work, but also space for more industrial uses for the robotics companies. Timber was chosen for this project mainly for its biophilic properties, bringing natural warmth, natural texture, and a natural material into the workplace, creating that indoor-outdoor connectivity. This project has also allowed us to think about how we design the connections in timber projects. It uses mechanical joints, we can make them accessible, and so we can start thinking in a more circular way. thinking about how the building is constructed on day one, but how it can be adapted over its lifetime. How can we add to the building? How can we expand it? And ultimately, how can we imagine its end of life? And how can the timber be reused in the future? The Sydney Fish Market is a new project on the waterfront in Sydney, Australia. It is a working fish market. And here the challenge was to take an existing fish market and think about what it can be now and in the future on a public waterfront with public access and public amenity. Here, the design focused on what the relationship programmatically is for the industrial uses, but also what does it mean to be a building on the waterfront today? How does this building act in service to its context? And so here, the design of the roof focused on capturing rainwater. A fish market obviously uses a lot of water. And so by capturing rainwater, filtering it, and also adjusting the programmatic use of water through advanced water efficiency methods for the fish market itself, we anticipate a 50% reduction in water use. This is a doubly curved roof structure. And so we worked very closely with our engineers to design and optimize the structure such that it can be constructed with simply supported beams and columns on steel, simply supported timber beams on steel columns. And so here we chose timber, both again for its natural texture, natural warmth, and biophilic properties, but also because timber excels in marine environments. And so here we were really leaning on the natural qualities of timber in this context. The last project I want to run through very quickly is the Key Quarter Tower in Sydney. The use of mass timber is an excellent way to reduce the embodied carbon in a building by preventing preventing sort of the manufacturing emissions due to concrete and steel manufacturing. Another strategy that 3XN is really committed to exploring is the reuse of our existing building stock. For the Key Quarter Tower, we were tasked with modernizing a high-rise. How do we humanize a high-rise building? And also, how do we reuse aspects of an existing building in some way? The AMP Tower was built in the 70s. It's right sort of down in central Sydney near the Sydney Opera House. And so our team undertook the challenge of trying to reuse as much of this building as possible in our new design. This is the new building. It was completed in 2022 and is fully leased, which is very exciting. But even more exciting is we used the entirety of the existing structure, including the elevator cores. We declad the building. We expanded the footprint by 50%, doubled the occupancy. And in the course of that effort, we were able to save 12,000 tons of embodied carbon. And so this is sort of another approach in tandem with mass timber that we think is a really important approach to designing for carbon. Thank you very much.
Talk loudly. Oh, I can do my. We got 30. Okay. Hello. All right. All right. There we go. That's better, right? So at StructureCraft, we're both structural engineers and builders. And the craft actually in StructureCraft comes from master craftsmen. The true expert that's involved in all aspects of the project really gets the hands dirty, looking at mock-ups, testing. And so this is our founder, Jerry Epp, with a mock-up of a very unique connection node for the Dinosaur Museum in Alberta. But it's this idea of starting from a structural sketch and moving on through the design process, knowing how you want to build it. This is a pedestrian bridge in Banff that we did. And this is a deceptively complex connection, right? But how these buildings go together and how these structures in the elements, lessons learned are actually taken into the structural design process. So there's a finished shot of that bridge in Banff. But this concept of the master builder is actually not new. A lot of the designers of the past were much more involved with the construction of their designs. We tend to work nowadays in, architecture, engineering, and construction. And I think innovation really happens when we start breaking through those silos. So for example, Frey Otto studying these forms, hanging models for his Munich Olympic Park, right? Or Gaudi and his hanging chain models, where this idea of anything that's in pure tension, you flip it upside down, could be pure compression for his Sagrada Familia in Spain. Or Robert Millar for his bridges. This is the Sagan-Tobel Bridge in Switzerland, of actually how you build something like this in the Swiss Alps without modern day technology. Okay, thanks. A little louder. Thank you. But I think in timber design, this is very important because timber a lot of times is exposed. It is going to change shape when you're out in the rain, right? And if you mess up, it's hard to fix without it looking horrible and having people like Catherine call you and yell at you, right? So it's tempting in the consulting engineering world to just performance spec that like you would precast to someone who will design it later on. The risk with that is that you may get further down the road and into CDs and have to say call timeout because it's too expensive, it's not buildable, and you have to redesign the connections. But if you're an engineer build type setup and you have that mentality, you understand how it's actually supposed to be put together, the tolerances in the field, and can start designing that from the get-go. So it's a way of actually taking those types of lessons early in design. Whereas if steel and concrete, a lot of times you can just size the members and you know you'll be able to make the connections work in the end. So we do projects all over the world, a lot recently in China, but mostly in the United States and Canada. And we've done a lot of mass timber office buildings and some hotel and multifamily, but over 5 million square feet in the past 5 years. So sprinkled around the United States, we've seen a lot of action in the Southeast and in Texas along the East Coast. And we do different types of projects too. So we do a lot of parametric modeling and analysis where we can do free form and custom architectural type solutions, both non-structural, cladding like in the Calgary Library, or structural. Timber footbridges, which is a big passion of our founder, Jerry Epp, because he doesn't have to worry about coordinating with the mechanical engineers. I apologize if there's mechanical engineers, but I can see that. And then these sort of grid shells and long span structures like these botanical domes in China on the top right, recently constructed University of Idaho basketball arena in the lower left. And then the Richmond Oval that was for the Olympics, it has this innovative wood wave ceiling that's both structural and acoustic. But like I said, in this sort of mass timber, what I would call like orthogonal type post and beam type structures, a lot have been completed all the way from Pacific Northwest into the Midwest and also in Texas and the East Coast. With a lot in construction right now, we're doing a project that's Southern Yellow Pine in Atlanta, and then some higher ads at Johns Hopkins, Princeton, and then a pavilion that I'm personally working on in Washington, D.C. in the lower right. But I want to take a quick moment to highlight this project because we have a model of this that we can see later, and I'm happy to talk to anyone about this. This is the Tianfu Architectural Expo in China. There's only a model of one of the vaults, but there's 5 of them. It's 800,000 square feet. It's the largest timber structure in Asia and one of the largest in the world. And to actually create this, one of the reasons I like to pick this too is actually if you take this model or the structure and you flip it upside down in that spirit of the hanging catenary, it becomes pure compression. That's actually these shapes. And that was important because that allowed us to make very simple splices in order to erect this much faster, is actually happening during COVID. And it's also utilizing steel. So it's a hybrid structure to create spans up to 450 feet and 150 feet tall. So some of those ideas might actually come in our panel that's coming up, the questions. So thank you.
So we're going to start the question and answer session. We have some questions that we've devised for the panel here. There's also someone taking questions in the audience here somewhere. There you go. And some questions as well from our online folks. So I will kick this off. My first question here is for Ricky. Explain the significant impact that embodied carbon of construction has historically held, and how specifically does the use of mass timber provide a positive solution in this context? What are some ways in which we can tangibly track those sustainability benefits using metrics and third-party validated standards?
Yeah, great question. And Catherine alluded to some of that in her presentation and some of the metrics that they're tracking on their actual projects. But maybe for context, and when we say embodied carbon, and to back up, when we look at, overall kind of the term sustainability of construction, traditionally going back 10 or 15 years ago, we've often focused on the operational energy, meaning what does it take to run a building, heating, electricity, cooling, air ventilation, all of those things, and how do we draw down the energy required to do that? Which is a great place to focus kind of that energy, if you will, is reducing that operational energy. But perhaps even what is very much sooner that goes into a building is the embodied carbon of the materials that it takes to build the building from day one. So what did it take from an embodied carbon perspective or a carbon emissions perspective to dig the hole for the foundation, to pour the foundation, to erect the structure, to place the finished flooring? All of those things have an embodied carbon or carbon emissions associated with them. So by using materials that have a lower embodied carbon in the construction process of the building, that's a way to have a big impact on the overall sustainability of that project from day one. In terms of how we can kind of track those things and how mass timber can benefit a project in that regard, we know that as a tree grows, it takes on carbon dioxide, gives off oxygen. That carbon dioxide stays in that wood when you cut the tree down. You turn it into a 2x6. You take that 2x6, turn it into a CLT panel. That panel goes into the building. So throughout that entire process, that is basically holding on to that sequestered carbon. Wood by dry weight is about 50% carbon. So all of that carbon is in the building as it's built. And you also account for the fact that it's typically much lower carbon emissions to actually manufacture those products than it would be to alternative structural building materials. So those two things combined is really how you have a significant drawdown in the embodied carbon. And like Catherine suggested, 40 to 50% reduction in embodied carbon is very common for mass timber relative to other structural building materials. And how do we actually put metrics to that? There's a number of ways, but I think probably the most comprehensive way is what's called whole building life cycle assessments, where that's looking at tracking those materials, every single material in the building from the time that they were kind of taken from their initial source, the manufacturing process, the transportation process, and the building erection. In some cases, those studies actually go through the end of the life cycle of the building and looking at reuse and recycling. So there have been a number of LCA, whole building LCA studies on mass timber projects, and similar results showing anywhere from a 40 to 50% reduction in some of the metrics associated with LCAs, like global warming potential. So those are some very kind of tangible ways to track those metrics.
Thank you. Do we have something from out there yet?
Did you want to answer a question from here? We have a question from Arthur online. What is theoretically the tallest we could build using mass timber? And are there any particular structural issues at great heights that might not be present with conventional concrete steel structures?
I can take that. It's a good question. I think, and it also plays into this concept of hybrid structures, right? If we're building taller and taller, most of the structural system is in the floor plates. And as mass timber, if you're building one floor that's 2 feet off the ground, you wouldn't do it 2 feet off the ground, but you know what I'm saying? If you do it 180 feet off the ground, it's the same. What's really the difference is the columns and the lateral system. And at a certain height, that's where actually steel or concrete makes a lot of sense, right? Otherwise, if you're trying to jam in the solution at a really tall height with mass timber for all the elements, you may see gigantic columns at the base or unrealistic lateral systems, right? So the answer is there's nothing really stopping us. I just think personally, as we get taller and taller and taller, you're going to see more and more hybrid systems to make those heights work. but you can still, from a four plate system, you could do mass timber all day long. Oh, the sweet spot?
Could you repeat the question so the people online could hear it?
I didn't mean to interrupt. It was just an augment to the prior question. What do you consider the sweet spot where a full mass timber height then sort of borderlines to requiring a hybrid solution?
That probably varies versus if it's in seismic, let's say, or not. So let's just say non-seismic to make it a little simpler, like in the middle of Texas. It's probably in the range of I would say 20-ish stories, maybe a little bit more. I think when you're getting a little bit more than that, then your columns you might want to look at potentially something else, right? Like a steel column. And doesn't have to be the whole height. You can transition it to timber as you go higher.
Do you think a super tall eventually could be a hybrid where you have?
Yeah, absolutely.
Where the mass timber is at the very top or the top third and the rest of it's?
Yeah, I mean, what I could see is a super tall skyscraper, right? Where the floors are mass timber. You probably have concrete topping for your diaphragm. It's connected to a very robust concrete core. You can just keep going, right? So, and then for the columns, maybe at a certain point you transition to a steel column near the base or concrete or precast. Yeah.
Thank you.
All right. How about Catherine? What's the real carbon impact of timber construction? How do we account for proper land management, reuse of timber at the end of a building's life cycle? How are we accounting for what happens in the forest? Its impact on carbon, proper harvesting, biodiversity, managed forests, old growth forests. What do you see?
Maybe I can speak to our approach to thinking because I don't think I have the answer to what is, proper land management. But I think seeing mass timber as a new technology, we have built with wood for as long as we have built things. Mass timber is a new again technology. It has required a great deal of innovation, and we're all starting to get used to it. And what that does is give us an opportunity to influence how it's executed now and in the future. And that for us, for 3XN and GXN, that requires circular design thinking, right? We're trying to think about the end of our buildings' lives, how we're reusing material. That also requires thinking about how our raw materials are being sourced. And so thinking very long and hard about the types of wood that we're using, the ways that we're sourcing it. The building industry has an opportunity to really influence how the wood is coming into our industry, how we're sourcing it, the sort of requirements that we're placing on this product. But I think also very significantly designing in the building's end of life, thinking about how we can take apart our buildings. As Ricky was mentioning, timber stores carbon, right? It only stores it as long as it is timber. And so the longer we can reuse that material, whether it's in a building or in furniture or in some other reuse, the longer that carbon is going to be stored. And so that's really how we're starting to think about mass timber as a building technology and a tool is as part of this circular system, as part of a bigger process than just the building that we're designing.
Any questions in the audience here?
Thank you. So timber is a finite resource, right? And it seems that there's a ton of buildings now and more that are using it. Do any of the panelists have an idea of like a projection? Are we going to run out of it, or because it doesn't reproduce as quickly as we might want it to? So I'm just wondering if you know how much longer we have, or how do you see that?
There's actually one of the posters in the exhibit that answers your question exactly, where it shows a map of the kind of the traditional timber harvesting, growing and harvesting regions throughout the country. And it shows the disparity of growth rates versus harvest rates. And then also even shows projections of, increased mass timber use and timber use in general over the next, I believe, 12 or 14 years. And even with that impact, there's still a disparity. Factor in also the fact that as you are harvesting trees, harvesting wood for use, there is a replanting protocol that you're following. So there is that factor that goes into it. But I mean, I think I would definitely check out that chart. I think it shows a great story of the fact through a study that was done that there is ample supply.
So for Kevin, you started to talk in your presentation about UL and the testing you do. Can you discuss a little bit more about the important role that testing has played in the adoption of mass timber? It's kind of a chicken and an egg relationship. Explain the context of this testing and how jurisdictions and codes have evolved to recognize the new materials and the results of your testing.
Yeah, so that's a good question. Thank you. So, the average person you walk up to and explain this to that's not familiar with this, it's an interesting scenario, like, oh, wood, doesn't that burn? But the test I described earlier, the E119 UL263, there was a multitude of tests done with mass timber on that. And then the test that Ricky described, the compartment test, the pictures that you saw, all of that leads to that calculation method that I went through. So wood is not new in fire resistance construction. A common, like your average gypsum board, plasterboard, wallboard, 2x4 with gypsum board on each side, or a floor that's made of 2x10 lumber and plywood on top and a gypsum ceiling on the bottom. That's not mass timber. That's like called stick construction, but the fire resistance of that has been around for at least 50, 60, 70 years. So the fire resistance of wood is not a new thing. But as Ricky showed, it has gotten into the building code, and it's slowly getting adopted more.
We have another question from our online audience. Gail wants to know, these buildings look wonderful, but they look a lot like non-timber buildings. Do you think that in the future timber will change the look of buildings and building typologies?
Maybe I can take that one. I think the answer is yes. I think we don't know how yet. I think the technology is something we are innovating as we go. I agree, a lot of the buildings do look like typical buildings because they're using a typical gravity structural system. And I think the more we learn about the capabilities of timber in terms of the different types of connections that we can make, the innovation with the different connection materials, we'll be able to push the architectural design further. I think one important aspect of timber currently in our buildings is that it is a natural material and we are being able to expose it. And I think that fundamentally changes our spaces. And so whether they look different or not, they certainly are different and they will operate differently because of the biophilic properties of timber.
Question is is a amazingly beautiful and traditional at the same way technology, but every time we talk to potential clients about this, they say that's an innovative thing and they put a big cost tag into this. At what point or you think this is going to evolve into something that may be more standard for not adding a cost, or if there's any region in the country or in the world that is already assumed to be a standard technology that there's no additional cost associated with?
Some of that, I mean, from our perspective, as a material component supplier, that's what we're trying to move folks towards is standardized connection systems. We often get asked, what's a typical connection for a wood-to-wood connection? And the industry right now is everyone's still developing something new on almost every project. What we try to do is look out there, see what are good ideas, and see what can be replicated and mass produced, pre-engineered, off the shelf, ready to go towards that, maybe not standardization, but more simplification of some of these detailed connection systems. So that's what we're trying to help a little bit in the industry.
Yeah, and I think from my perspective too, just in terms of the cost, to your cost question, a lot of it is tied to what Leaf was saying about hybrid systems. And that is the whole goal with that is using each material where they work the best, where they're best suited for. So understanding that and understanding it's very different if you're looking at, a project like T3 versus a high rise versus a 2-story school. What are the efficient spans for mass timber, and can you design the building around those as opposed to how does a typical school lay out, and can we make a mass timber solution work there? So it's designing to the specific strengths of each material. And if you can't do that, if you can't design to the specific strengths of mass timber, can you utilize, a hybrid system for the beams and columns and use a mass timber floor panel on top of that, for example? So there's ways to look at it from both angles. If you're really looking to maximize the amount of timber used on a project, I would definitely recommend designing around the strengths and parameters that mass timber as a material has.
Can I sit? Hello? Yeah, I got the problems with it. So there's a couple parts. One is the cost of just the material, which is a little bit out of our control, but and it relates to what I was trying to say earlier is that if there's a design, let's say the design team is working on a design, they're in DD and they want a price check and they just sort of throw it over the fence to a contractor, there's inevitably that fear factor and bump you're going to get. But because the devil is in the details with timber, you want to have the people involved early in making those connections that are buildable and economical early. Right. So it's a front loaded process so that you can get that checked throughout the way. Because the other part of this is that there's a whole busy fabrication market, and you don't want to go too far down the road and realize that you're too expensive and then you lose your queue to get to site on time. Right. So everything is sort of front loaded. So a short answer would be make sure everything is designed further than you would think it would be for schematic design and DD because of that exact reason. Right? Get the right players on board, get it priced so you don't have the throw over the fence fear factor.
I have a follow-up question to that. We've seen beautiful projects all over the world. Are there certain municipalities or cities that embrace this more and cut down on the permit approval process or the testing that may need to happen with this technology?
I can address, at least in the US, what we've seen. It's definitely been a wide variety. I can't say that any one specific city has been incredibly difficult to work with. There are different levels of what types of information they're looking for. Some of it is if you're looking at doing a project that very closely follows the prescriptive code guidelines that I talked through, then it oftentimes is just basically, if they're not up to speed on those, showing them those. But oftentimes projects are looking to go beyond those, or their jurisdiction hasn't adopted them yet. So it's a specific conversation with them to help them understand the testing that we've showed and that Kevin talked through, and help them understand what information is available to them. There are certain jurisdictions, I think of like the city of Boston and other cities are looking to do this, where they have stated goals as a city on reductions in embodied carbon, and as a result, one of the things that they're doing is working with Softwood Lumber Board and U.S. Forest Service to create basically an accelerator program to provide some incentives to projects using mass timber in those cities. So those are a couple of examples, but I think it really comes down to understanding what the goals of a project are, and then understanding what the concerns or just questions from the city's perspective are, and just having a very early conversation with them in the design process.
Hi there, Craig Applegath. Great presentation, folks. I'm an architect in Toronto, do mass timber. Our project's down below in the exposition. Question: what would you say to a client, there may be some client types in the room here, about why they want to do mass timber now? What's a one thing you would say, do mass timber now because?
It's a good question.
One thing that I would say. I'll go in the meantime there.
real quick, the developments that we go to around the country, people will walk into a building, they touch the wall, they feel the wall, they embrace the space more so than you get any other type of construction system. So that would be my short answer.
Yeah, they're,
Okay, I'm
I
back.
mean,
Oh,
we're just going to say the proof that we've had from buildings that have been built is that they occupy faster, they occupy at higher rents. They not only do they do that, but they bring people in. I mean, they're almost an advertisement for themselves. Right now, that's what it is, right? Every new technology has early adopters. That's why they're early adopters, right? Because there are specific advantages. They're going to pay for them a little bit upfront now, but those advantages are from the outset of a building. I'll ask the last question tonight. So kind of with all the things that we've been talking about, crystal ball time, where are we in 10 years? What's the capacity that we've built up for fabrication? What is the sweet spot for a building that height? Where are we going? What's the industry heading to?
I think from two parts, from the sustainability aspects and the biophilia, that I think we're not gonna see this decline. The one thing I was gonna say earlier is that because I'm in Seattle, and every summer and fall, it's now a normal thing to be bombarded with smoke from these super fires, right? And there's a great TED talk, I'm gonna plug it, from Paul Hesberg, that talks about this. But our forests are like 3,000 trees per acre, and a healthy forest is like 800, right? We actually have a lot that we need to harvest just to improve what's already there, right? And then we can take that timber and use it in our building structures. And so there's a tremendous trickle effect even to the watershed. It's a powerful story for even a client as well, but that is a reality that we faced, right? And when you are faced with things like that, then it's not a fad. So
I'm really excited to see what happens with the acceleration of mass timber and multifamily developments. It's been one of the, initially when mass timber, I kind of showed the graph, 2011, 2012, mass timber was actually pretty seldomly used in multifamily developments, but that has been something that has really grown rapidly. And so I'm kind of excited to see how that continues to grow, more affordable housing, workforce housing developments. To answer your question, Craig, speed of construction is another benefit with mass timber. And that's certainly, we need a lot of housing. We need a lot of housing fast. So mass timber is a solution to help solve some of those challenges.
Want to add something?
Sure. No, I think thinking about sort of crystal ball in 10 years, we think a lot about the hybrid structures, right? And that mass timber can become simply another tool in our toolbox for sort of the best use of timber in any type of building we're designing. I think the aspects of timber that to us are really difficult to ignore are the natural quality, the texture, the warmth, the smell. And so, as you were mentioning, people go and touch it. I've walked into T3 Bayside and that was the first thing I did. And so I think timber's ability to kind of improve interior environments is a really huge benefit. I think carbon is something we just can't ignore. And I think globally, we're seeing cities and jurisdictions starting to develop low carbon design guidelines to require a reduction in embodied carbon. And timber inherently assists us with that. And so I think as we continue to innovate mass timber as a building technology, carbon is going to be one of its sort of strongest qualities.
Right. And with that, we'll end the evening. Thank you, everyone, for attending. Thank you, panelists.